Okay. Well, thank you. It's a great honor for me to be able to speak to such a distinguished audience about things. I should say the title I think is the same as I gave, but I did it from memory. It's the first time which I've talked about the relationship to dark matter. It makes a very specific prediction as to dark matter, but I've never really talked about that before, so that's what will be distinctive about this lecture. Sorry about using this modern technology here, but I hope people will get used to it. Now, first of all, this is just a picture of the universe. Now, this picture of the universe is perfectly conventional and standard and everything. You might wonder about all the wiggly stuff at the back, but that's because I don't want to commit myself as to whether the universe is open or closed. Although there is, most of what I want to say doesn't make any difference at all, but there is a slight, I think it probably works better if it's either closed or flat and not the hyperbolic case, but that's not quite clear. There's some things to be worked out there. Anyway, this right from the bottom spot here to infinity is perfectly conventional lambda CDM cosmology. There's a little bit thing about the little tiny point at the bottom, which is where inflation ought to be. You might say, why I don't put inflation in the picture. There are two reasons. One is maybe I did, because it would be simply in that little spot at the bottom there, and you wouldn't see it. But the other point is that I don't really believe it, and I think that something else which plays the role of inflation has to be present, and I'll say something more about that later. For the moment, let me just make one comment. I mean, I know there are lots of reasons for inflation, and some of them are good and some of them are not so good. One of the ones which I regard as not so good as that it is supposed to smooth out the universe and make it very flat and so on. And I never believed that one for the sort of reason which I'll show you here. You could imagine a universe which is collapsing, so the time is going up the picture, but you introduce a few little irregularities, and those irregularities would grow and grow and grow until they form black holes which congeal and make one unholy mess at the end. So this would be a much more probable type of universe. And you can actually work out how much more probable by using the Bekenstein-Hawking formula for the entropy in a black hole, and that gives you the logarithm of the probability, and then that tells you how unlikely, since all the equations you could put in the inflaton field in just as well as everything else. Imagine there is an inflaton field in there and it will still do this. Then why don't you get this much more probable initial state? And the more probable it is would be something of the order of, well, and I say something order of at least as much as 1 in 10 to the power 124. So the unlikeliness of this is something very extraordinary. It's interesting, of course, when, because we're honoring Lemaitre in this meeting here, and Friedman and Lemaitre, who produced solutions of the Einstein equations, would never have been able to solve the equations, of course, if it was something like this. But they made the assumption that the universe was isotropic and homogeneous, which was a very good assumption if you want to solve the equations. Doesn't necessarily mean the universe was like that, but it does seem that it fits pretty well, which maybe was a happy accident, but the model at least is a pretty good first approximation to what the universe does. Well, we're here, we've got a positive cosmological constant to produce this exponential expansion in the future, and this all seems to be consistent with what we see. So I'm not quibbling at all about lambda cold dark matter model. All I'm quibbling about is the very beginning, which may be something a bit different from inflation, although there is in my scheme something like inflation, and I'll come to that a bit later. But first of all, let's do a little bit of mathematics, which can be done in all these models, the Lemaitre and Friedman models and so on, and the others that people played around with. I'm going to do two mathematical tricks to this. Mathematical trick number one is to squash infinity down until it becomes a smooth boundary. Mathematical trick number two is to stretch the Big Bang out until it becomes a smooth boundary. And as long as it is one of these standard models, you can certainly do that. When I say squash and stretch, well, the squashing down of infinity is very much like what I think Renata did in her lecture, producing a nice Escher picture. This is it's commonly known as the Poincaré disk, but since we're more or less in Italy, I think it's more appropriate to name it after the person who really did do it first, which was Beltrami. Beltrami had so many different models. The trouble is that if you say the Beltrami model, it could be one of about 4 different models. But this is certainly one of them, and he had it a long time before Poincaré. So that is the Beltrami conformal model. And conformal here means, of course, that the mapping to the Euclidean plane is a conformal map. And you can see it very nicely in this first of Escher's circle limits, because the fish, I think they're fish, the eyes of them are circles, and you can see no matter how close to the edge you get, they remain exact circles. And conformally, the conformal would be normally the angles, say the angles on the wings of the fish, or whatever fish have, fins I suppose, that the angles are correctly represented no matter how close you are to the edge. So it's basically, the smaller you get, the squashing down is isotropic. But the feature that's particularly nicely demonstrated here is that as far as these fish are concerned, this boundary here is infinity. But as far as we're concerned, you can think of this the same Euclidean geometry, but I mean, it's a different conformal factor to get to the geometry here. With the geometry here, where you have to have a conformal factor where the fish think they're the same, no matter how close to the edge they are, as far as we're concerned. It's a very uniform geometry, but the infinity of this universe is represented as a finite boundary. And not only that, you could imagine that you could conformally, perfectly consistently step outside this model and extend the conformal geometry to outside. And so these ideas are things that we are going to carry over to the space-time picture. And so that's what I'm doing here. I'm squashing down infinity to a conformal boundary here, just like in the Escher picture, and I'm stretching the Big Bang out to make that a conformal boundary as well. And these things work fine in the exact models. There is a question about what happens, well, that's the words about what it's doing here. Question about what happens when you introduce irregularities, which I'll come to in a minute. But before doing so, let me just be a little bit more explicit. What in space-time terms conformal means, what it really means is you preserve the light cones. So that's what's going on. The light cones, of course, or the null cones are the important thing, first important thing in general relativity. But the cones don't give you everything. They don't give you the scale. So you have the cones, roughly speaking, give you 9 of the 10 components of the metric per point. It's really the ratios of the 10. And the 10th component is the scale. So I've kind of distinguished these here, but the scale being represented by these hyperboloid surfaces here, which are the various, imagine, identical clocks, and the ticks will be represented by these surfaces here. And the point I want to make at the top here is that we have now extraordinarily precise clocks, and the precision of the clocks that exist really comes down to the fact that we're using two of the most fundamental, or the two most fundamental equations of 20th century physics, one being, of course, Einstein's E equals mc squared, and the other being Max Planck's E equals h nu. One of them tells you that energy and mass are equivalent, and the other tells you that energy and frequency are equivalent. So you simply put those together, and that tells you that a stable, massive particle is a clock of extraordinary precision, because that precision is based on these two very fundamental laws. And so it's really that tells us that we have such precise clocks. But another point I want to make here is that if we think of space-time as being given to the first structure of interest is the light cones, and you can talk about black holes and so on, and how particles or light rays behave particularly, and a lot of physics gets away with only this structure. Most particularly Maxwell's equations are not interested in the scale. They completely work no matter what the scale is. And this is also true if you think of the Yang-Mills equations as classical equations, and if you don't have any mass, you're just looking at the Yang-Mills equations. They are again just as conformally invariant as Maxwell equations. It's when you get mass in that you have to start to worry about the scaling, and then this is the geometry that you need. And so Einstein needs the full 10 components per point, whereas a lot of physics gets away with the conformal structure. So I'm going to try and concentrate on that point and take the view that okay, if you don't have mass around, well, then the conformal geometry is the important one, and it's mass that gives you the scale and gives more structure to the space-time. Okay, so that's the picture here. Another point I want to make is if you don't have mass, or if you don't have anything to do with mass, and of course Einstein's general relativity is interested in mass because that's the source of gravity comes from mass, but many other things in physics depend on having mass, and then of course you would need the picture with the scalings as well. But if you don't have mass, then the conformal picture seems to be really what physics is doing. So that's a point I'd want to stress here. Now let me make sure I don't lose what I want later on. Well, I may have lost it already, but anyway, yeah. Now suppose you do have irregularities. I have to make sure, again, I don't lose anything. Here we are.